Okay. You can see me. Okay, well, that's part of the way there. Okay, so it looks like we're not going to have the intro. So we'll go on without that. But we will start with, I believe, the Jordan's workshop that he's going to do right now. Hopefully the audio works on that. And do we have Jordan, or are you still trying to figure all this out?
I am here and I'm still trying to figure out what is going on. So the video does have audio, actually both of the videos, everything has audio, but for whatever reason, the streaming software, it's not coming through when we actually start playing it. I have no idea what that is about. So I'm still looking into that. Give me just a couple more seconds here. We can try that intro one more time, and if that doesn't work, then we'll find another way.
Okay, yeah, that's a shame. It looked like a great video. Do we have the CKBull team here?
Let's see, CKBull team should be coming on in about a half an hour or so after the first workshop to do theirs.
All right, so they won't be here for right now. Yeah, thanks everyone for their patience. Okay, you're on right now.
Hello everyone, and welcome to the CKBull Hackathon. My name is Jordan, and over the next few minutes I'm going to be talking you through what this hackathon is about and give you the information that you need to participate. The official challenge of this hackathon is to build something exciting with the CKBull Signer API. That choice is completely up to you on what you choose to build, but before you make that decision, you need to know what the CKBull Signer API can do and what the judging criteria are so you have the best chance at winning a prize. So what does the CKBull Signer API actually do? First, it allows users of the CKBull mobile app to sign into a dApp with their address as their ID. Second, it allows users to transfer CKB from one address to another. And third, it allows users to sign and execute smart contracts. To help developers with this, CKBull has created a developer console for you to manage your dApps, a REST-based API to easily integrate with, and an API playground to help you test the functionality of your dApps. The CKBull team has been hard at work to make the developer experience easier and lower the barriers to entry. There's still a lot more work to be done, but once you start using these tools that they've built, you'll quickly realize that their efforts have paid off, and these tools make the entire process remarkably simple. Next, let's talk about the judging criteria. The first is technical completeness. Judges are looking to see that your project demonstrates proper usage of the CKBull Signer API and that it's been incorporated in a meaningful and fitting way. They will also be looking at how much of the core functionality of your dApp is up and running. Not everything is expected to be completed, but of course, the more the better. The second is ambition. Judges are looking to see if your dApp is attempting to accomplish anything technically challenging. Difficulty is absolutely not a requirement, but if you are trying to do something challenging, the judges will take that into consideration. The third is design and user experience. Judges are looking for a dApp that is user-friendly, easy to use, and attractive to users. This is a hackathon, so nothing is expected to be final, but the more that you can demonstrate during the competition, the better. Let's talk about the prizes. There's a total of 1.5 million CKB up for grabs. First place is 750,000 CKB. Second place is 375,000 CKB, and third place is 225,000 CKB. There's also 2 more prizes of 75,000 CKB for project submissions that deserve an honorable mention. All prizes are subject to the discretion of the judges. That means that anybody who's caught trying to cheat or undermine the good intentions of the hackathon will be disqualified. So please, behave yourselves. The hackathon has officially started today, Monday, August 21st at 12 o'clock p.m. Eastern Time. The cutoff for all hackathon submissions is Sunday, September 3rd at 11:59 p.m. Eastern Time. There is no guarantee that late submissions will be accepted, so please make sure all submissions are completed at the designated deadline. For all participants, we highly recommend that you join the CKBull Telegram channel so that you can get all the latest information and get help from the CKBull mentors. Their hours of availability will be posted so everyone knows when they're online. The CKBull Telegram is also a great place to discuss your project with others and find additional team members if you still have roles to fill. Time is short and we need to get the workshop started. But before I move on, I want everyone to remember that a hackathon isn't purely about competition. It's also about community, camaraderie, and of course having fun. Good luck to all of the participants and may the best app win.
Okay. All right, so we'll now have Jordan's workshop, I believe. I think we're hopefully past the technical difficulties now.
Yeah, I think we're past most of it. So just give me 1 more minute here, and I'll have that get started. I just got to load up slides and stuff.
Good morning, everybody. Welcome to the CKBull Hackathon CKB Crash Course. My name is Jordan. I'm a senior software engineer at the Nervos Foundation. I've been a software engineer for a little over 20 years. I've been in the blockchain space since 2011, and I've been with the Nervos Foundation since 2020. Taking a look at the agenda today, the target audience is developers participating in the CKBull Hackathon who are new to Nervos CKB with some familiarity with Bitcoin UTXOs and Ethereum smart contracts. So if you are an Ethereum developer and you're not familiar with UTXOs, my advice is to just go ahead and go through this video. I'm going to try to make it a little bit easier and stay high level, but ultimately if you feel like you need it, maybe after this video you go back to YouTube and Google something up just about basic UTXOs. It may help you a little bit. So let's see, the first thing we're going to be going through is I'm actually going to give a very small introduction to UTXOs from the standpoint of what it means to a developer. Then I'm going to give you an introduction into CKB, the main blockchain itself. Then I'm going to go through the cell model, which is the programming model that's used on CKB, and this is specific and unique to CKB. It doesn't exist anywhere else, and it's very different from Ethereum. And then lastly, I'm going to give you a couple of resources that you can use to get started. But I want to state this ahead of time, CKBull will be having their workshop after this one, and you absolutely need to see that one. UTXO introduction. What is a UTXO in developer terms? Now, my definition is going to be a little bit different than most of what you're going to hear on YouTube because those videos are aimed at a high level but very general audience. This is also high level, but this is very much developer centric, and I'm focusing on less on what a UTXO is and much more on why it's important and why I actually believe it's relevant to blockchains. Now, a UTXO is an isolated state unit that can be used concurrently with other UTXOs. So it's an isolated piece of state and it enables concurrency. Concurrency is really the key word here. I'm going to explain that a little bit more. Why does this matter? The process for updating state data is read, update, write. Okay, so if we go back away from blockchains for a second, just go back to normal computer programming. Let's say you have a variable, the x variable, it's set to the value of 5. You want to increase that. You call the increase function. What is going on in your processor? It's got to first read the x variable. What is it? It's 5. Next, it's got to update it. It updates it from 5 to 6, and finally, it writes it back into the x variable, back into the memory, the main memory. This read, update, write process is going on in our CPUs millions, possibly billions of times every second. And this process is inherently single-threaded. It can only occur on a single thread. So to achieve concurrency, you cannot unify state. That's the main issue that UTXOs are actually solving. Under the account model is single-threaded inherently. The UTXO model is multi-threaded. Now in the graphic to the right here that I just threw this together, this is very much simplified, of course. So if you're looking at this and thinking, wait a minute, I already know this is really supposed to be simplified. So up at the top we have block 0, block 1, and block 2. Account model up at the top. In each one of these blocks, this account only has a single balance. It's one single piece of data. Every time it's just updated. You can see we added 100 and then we added 3. In each frame, it's just updated. Now, if you look at the UTXO model, and these are 3 different accounts here because they're different colors, so 3 different users. In the first frame, the blue, the balance here, the total balance is actually 300, but you see there's actually 2 pieces of state data, one for 100 and one for 200. So you actually have to collect all the pieces of state and add them up to find out how much this person actually has. Whereas below in orange, this person only has a single piece of state, and it makes it's much more simple. There's only one place to read, but that's not always the case. There's no guarantee in a UTXO system how many pieces of state actually exist for a single user. And so if you look at what blue did in the next block, he actually consolidated it into a single one, while orange did the exact opposite and split it into 2 state units. Now, this type of expansion and construction is going on all the time in UTXO-based systems. This is how it operates. And so in Nervos and CKB, there's actually millions and millions of UTXO-based states that are out there. And we call those cells, by the way. There's millions of cells that are all alive at any given time, and they're changing every block. Now, this is where it gets interesting. So if you look specifically at orange, and I'm going to give you a real simplified version explanation of this, is you see that orange has 2 different pieces of state in block 1. And what this is enabling is that when they're going into block 3, so orange actually sent 100 to blue and then kept 100 left over as change and then sent 100 to green. Because orange had 2 different state units here, they're able to do this read, update, write process twice as fast as it could occur on the account model because they are actually separate. Now, of course, there's a lot of nuances to this and everything, and different optimizations that are going on in the account model and things that have to be considered in the UTXO model, but this, in its simplest form, is why the UTXO model is something that we're actually pursuing. It's because we can execute in parallel. When you split up the state into multiple independent pieces, we can now go parallel, and we can go parallel in a very big way. Okay, so what is Nervos? Nervos is a modular blockchain network built from the ground up to ensure outstanding security, decentralization, flexibility, and interoperability. What is CKB? CKB is a flexible and interoperable layer 1 blockchain built on RISC-V, secured by proof of work. It's the foundation of the ecosystem. So I want to just quickly point out that Nervos Network is actually a multi-layer ecosystem, and we have EVM-based layer 2s. But today we're just focusing on the layer 1 blockchain, that's CKB, and that's UTXO-based. So CKB is UTXO-based like Bitcoin and has Turing-complete smart contracts like Ethereum. It's combining the best of both worlds. When you hear this, it probably sounds a lot like a lot of the other blockchains out there. The difference is that CKB is designed to actually do what a lot of other blockchains only claim to do. And they achieved this by creating better solutions to the problems that all decentralized blockchains face. So if you're looking for a smart contract platform with real decentralization, you're in the right place. And in the next couple slides, I'm going to try to give you a little bit better idea about some of the features that are involved that actually make this possible. What is special about CKB? Here's some of the features. The first is sustainable limited supply caps. So I'm sure you all heard in the Bitcoin universe the phrase, there will only ever be 21 million Bitcoin. Investors love that because Bitcoin is hard-coded to a maximum of 21 million coins, at which point there will be no more mining subsidies and the currency will effectively become deflationary. And this means that every coin that is being held is slowly going up in value because coins naturally fall out of circulation. So that is a great thing for investors. The same exact thing, it actually exists in CKB, but it's even better because in the Bitcoin universe, they haven't addressed how do miners get paid after that. It's kind of an open question. So the 21 million limit, it's kind of hard to say if that's actually true or not. With Nervos, it's a little different. It's both inflationary and deflationary at the same time. It's inflationary on those that are occupying state space. So if you are using the blockchain to store data, you are getting hit with a very small amount of inflation. That is being used to pay miners perpetually into the future. So miners are taken care of. Now, the part that's deflationary is if you are not occupying state space, if you are just a long-term investor, you lock your coins up in the DAO and it offsets that inflation one-to-one, making it effectively a fixed cap currency from your perspective. So it is deflationary. So it's really the best of both worlds there. And the tokenomics of Nervos are actually really great. It's what actually got me into this coin in the future. So if you are into that kind of stuff, I highly recommend that you, after the hackathon, when you have a little more time, you read into it. And we're providing some links to some of that stuff because it's actually a really, really great read. Yeah, the next one is NCMAC Proof of Work Consensus. So the NC and NCMAC actually stands for Nakamoto Consensus, which is Bitcoin's algorithms. So NCMAC is actually based off of Bitcoin's proof of work. Bitcoin uses 10-minute blocks, and that's great for security, but that is not a good user experience, especially if you're dealing with dApps. Your users do not want to have to wait 10 minutes. So the main innovation, there are several innovations in NCMAX, but the main innovation that I think is most relevant to developers is the variable block time. What NCMAX is doing is examining the network conditions, and it's basing its block time off of how the conditions are at that very moment. Now with Bitcoin, they use a 10-minute block because they're not considering what's going on with the network at all. They're just making an assumption that 10 minutes is guaranteed to be enough to propagate that block everywhere and process it and have everybody be in sync. NCMAX is a little different. It is actively looking at the network conditions, seeing how are these nodes connecting and can they safely decrease that block time without sacrificing security. So it's always adjusting, and typically we're looking at block times between 10 and 15 seconds. More recently I've seen them closer to 10 seconds, which is a very good user experience, especially for dApps. 10 seconds or 10 minutes, I mean, it's pretty much a night and day. Again, this is a pretty deep topic. There are other innovations here that I don't have time to discuss, so if you're into that, I'd recommend you click on this link later on and read more about it. Next is RISC-V based virtual machine. So on CKB, the virtual machine that executes smart contracts is actually based on RISC-V, which is a computer architecture. And so if you're not familiar with RISC-V, it's similar to ARM, which is in the processor in your smartphones, or x86, which is used in most PCs. So RISC-V is another one of those. It's an open standard that's being adopted worldwide in billions of devices right now. It's used in all kinds of things. It's embedded electronics, like it might even be in something like your television remote control. It's also used in supercomputers, and actually Google just announced that one of their next Android smartphones is going to be based on RISC-V. So it's an up-and-coming technology. The reason why this is important for a developer is that this allows you to have a tremendous amount of flexibility. You are not programming for a special little limited high-level environment. You are programming effectively on bare metal. Our virtual machine is emulating hardware. So you are making RISC-V binaries for hardware effectively. There is no room to go any lower level. This is giving you the maximum amount of power that you can ever have and flexibility. So, and this also has another advantage of all the tooling. This is an up and coming ecosystem. There's a lot of big players that are starting to invest in RISC-V. The tooling and infrastructure that's being built around RISC-V, we can use all of that, right? As developers, we get to piggyback off of that and use all of those tools, which are going to be much more robust and safer and build better smart contracts than if we were to go off in our own direction and do something experimental. So RISC-V is a great thing, another great innovation that we are able to take advantage of. And if you're interested in that, we've provided some more links to read more. UTXO-based cell model. So the cell model is a programming model that we use on CKB, and its origins are based in UTXOs, which means that it allows us to scale massively. So we'll be talking about that a little bit more in the next slide. Account abstraction and state rent. These are two major features that are up and coming in our industry. There's a lot of change that are kind of scrambling to find a way to implement these because both of them are so important. And both of these features have actually been up and operational in CKB since its launch in 2019. So we're going to be talking about both of these features a little bit more in the later sections, but they are absolutely some of the most important ones that are around today. And I'd also just want to point out that the Nervos Nation channel on YouTube, this is a community-run channel. They have some really great videos on all of these topics, and they're little 5 to 10 minute animated videos that really give all of these topics a great explanation at a high level. So if you're interested later on when you have more time, I highly recommend checking that out. Why is the cell model important? Account abstraction enables smart contract-based accounts. So I mentioned this before. Account abstraction means that instead of just using a simple private key, public key pair, you actually rely on a smart contract to manage accounts. And this is important for a lot of reasons. The big one is interoperability. And I'll give you an example of this. So let's say you have blockchain A, B, and C, and we're trying to do something interoperable where the user interacts on blockchain A and it triggers an event automatically on B and then on blockchain C. We can't do that today. And the reason why is because if you were to initiate an action on blockchain A, the user has to sign there. Then they have to go to the blockchain B and they got to sign again. And then they have to go down to blockchain C and they have to sign again. It's a manual process at every step. That's because it's been hard coded into the blockchain to only accept authorization through a key pair. So with account abstraction, all of that goes away. We can actually use smart contracts to automate that process so they sign at blockchain A and it automatically triggers the events at B and C in a very seamless, decentralized, and secure way. Now, this is the reason why it is so important, right? And this is the reason why blockchains right now are scrambling to try to implement this. I would say most of the blockchains in the top 100 right now are working on ways of putting account abstraction into their system. Nervos has had this since 2019, since the launch in 2019, before the term account abstraction was actually even used. So it's nothing new to us. And I bet if you actually go out there, if you do the research after the competition, you look out deeper into account abstraction on these other platforms, you're going to find that the systems that have been put into Nervos are probably the cleanest and best version of account abstraction that you will find in the industry today. Next, state rent enables sustainable low fees. So this is referring to the pay once, store forever model that a lot of other blockchains use, and it doesn't really make any sense. Why would a miner persist your data forever if they've already gotten your money and they don't have to? That's the problem. You've paid your fee, they got your money, and now you're asking them to keep this data safe on the blockchain forever, while the miner has continuous costs for energy, for internet, to replace hardware over time. It doesn't make sense, right? So at some point in the future, that model starts to fall apart, and they will not persist that data. They will end up just throwing it away. So this is why so many blockchains out there are trying to implement state rent, is because this is a model that is more sustainable. And in Nervos specifically, this actually is part of what enables super low transaction fees, because the storage cost is decoupled from the transaction cost. Because the transaction cost, that's just processing, right? That's a CPU processor, so it takes a fraction of a second to execute, and that can actually be offered for a fraction of a penny. While the storage cost is segregated, and actually when you take your data off of the chain, you get your deposit back. You put it on, you have to pay a deposit. You take it off the chain, you get your deposit back. And this is part of what keeps the entire system sustainable for everybody, including developers and end users, and also enables the system to keep fees very low for transactions, usually a fraction of a penny, and they will remain that way during congestion period as well. So state rent, another great feature that if you have more time, I suggest you read more about. It's one of the best elegantly designed state rent systems you will find out there, and it's been in Nervos since 2019, since the launch in 2019. UTXOs enable scalability through parallel execution. So I already mentioned this one a couple times. So UTXOs are needed for concurrency. So the CKB is designed to be a layer 1 blockchain. You can already see that it has a lot of flexibility in it, which really makes it great for interoperability. It also has a lot of sustainability features in the tokenomics like state rent and a few others, which make it really great for low fees in a sustainable way. Sustainable is the key here, because if it's not sustainable and the system falls apart in 3 or 4 years, how are you going to build anything on that, right? That's a single business cycle. You cannot trust those types of systems if they haven't been designed right, because they might not stand the test of time. So the UTXOs are also a big piece of this, because if you are designing this global foundational level of the blockchain ecosystem, you must make sure that that is scalable. And the way to do that is through UTXOs, and that's why the cell model, which is Nervos' CKB's programming model, is based entirely off of UTXOs, because it enables that kind of massive parallelization that we can take advantage of, especially in a future where computer processors are adding more and more cores, and we're able to take advantage of those to execute smart contracts in parallel and really give a big performance boost over the account model. First-class assets enable digital ownership and enhance security. So the simplest way I have of explaining this is that the user's authority always takes precedence over smart contract authority. This enables digital assets to actually somewhat mimic the way that physical assets exist in the real world. And I'll give you kind of an example of this. So let's say that there's a really popular NFT collection with some expensive NFTs out there owned by hundreds and hundreds of users. Hacker comes along, he gets into this smart contract, he's compromised it, and what he would do is then he would probably want to take all of these NFTs, he'd send them all to himself, then he'd take it to an NFT marketplace, dump them out there, sell all of them, liquidate it, and then run away with the money, right? That can actually happen in an account model based system. With first class assets, that can't actually happen. And the reason why is because the user's precedence on their own assets is something that the hacker can't get into, because their authority is above that of the smart contract. So it's kind of like having, let's say that digital asset, it's kind of like having it in your house, right? It's like you bought it from the store and you took it back to your house. Somebody broke into the store, doesn't matter. They didn't break into your house, right? They don't have your private keys. They don't have access to your assets. And because of that, the community as a whole can recover from this scenario much faster, because the hacker can't actually move things around. He can't actually steal anything. Like he can do some damage, right? I'm not going to pretend he can't. He can make it so the contract doesn't work right anymore, but he can't actually take anything. And because of this, like, why, knowing this, like, a hacker probably wouldn't even do it. It's a big disincentive, because like, why would they waste their time trying to break into a system when they can't actually steal anything? Okay, flexibility is a cornerstone of architecture. So I'll give a couple examples of this. Transaction fees can be paid by anyone and no any token. So this is kind of a big one, because in Nervos, the transaction fees are paid in CKB, but they can be paid, who pays them? It can be anyone. For example, it can be the user, the initiator, or it can be the dApp developer, or you can do some kind of crazy things, like you can actually attach CKB to an NFT, and then whoever possesses that NFT already has the fees to move that NFT around in the NFT itself, and they don't actually have to add anything to it. Or a better example is probably if you're a dApp developer and you issue your own token, you sell your own token to a bunch of users, and you want your users to only have to have that token to interact with your dApp. So they can pay you in your own token to interact with your dApp, and then whenever you form a transaction for them, you actually can just inject that CKB for them, and that's a couple of fractions of a penny of in CKB, and that will enable, then they can just sign that transaction and they don't have to deal with CKB at all, right? They won't even know that it exists, and they and to them they're just purely interacting with your token. So it enables some really great flexibility features for the dApp developer. Next, template-based smart contracts reduce time and cost. So this is a big one. In the Ethereum universe, ERC20 tokens, we're all familiar with those. There's tens of thousands, probably hundreds of thousands of tokens by now. They're all copy and pastes of each other. It's the same contract deployed over and over and over again. This is a huge huge burden on the blockchain, and it's also very costly, and this time and cost all gets paid for by the user ultimately, so it's really increasing the cost in a way that's not sustainable. So in Nervos, the smart contracts are all template-based by default. This means that any user and or developer can just walk up to our SUDT smart contract. That's our single deployed smart contract for tokens, and they can immediately just mint a new token for a fraction of a penny. And so that's a huge savings of cost, and it makes the entire blockchain more efficient and sustainable because there's not a lot of bulk stuff just sitting out there doing all the same thing. We have exactly one contract. There's no reason to deploy another one. You could if you wanted to, but there's no reason to. And so that saves a lot of stuff, and ultimately the users are much more happy about that because it's keeping the cost low for them too. Next, smart contracts can be in any language that compiles to RISC-V. Now, officially, we support Rust, C, and Lua, so I would suggest you stick to those. But the reason why this is important is in the future, RISC-V is starting to be adopted by these big companies, like I mentioned earlier. Google is moving Android to RISC-V. There's going to be more and more support for this platform, and as that happens, more and more languages are going to support RISC-V, so there are more options for us to consider in the future for support and building smart contracts. And we're also able to take the advantage of the RISC-V ecosystem, which is a growing ecosystem, to build better tooling and also better, smart, and safer smart contracts in the future. And then any crypto primitives can be used without a hard fork. So this is a big one, and this is one of those that I don't think many developers fully understand enough to really appreciate. It means that the encryption, like SHA-256 and SECP-256K1 and R1, these different crypto primitives that are the basis for security on all blockchains, you can actually update them without a hard fork. They're handled at the smart contract level. And so this is important for two reasons. The first one is that all encryption over time gets defeated in some way, and it has to be replaced, right? This is an update process, and when these updates occur, it requires a hard fork, and it's a big deal. It can take months, sometimes years. It's just a big effort that you don't want to have to go through if you don't have to. The second is when when you're trying to take advantage of interoperability or features, you don't have to wait for anybody, right? And specifically with interoperability, there's every blockchain out there speaks certain languages, right? The encryptions that it supports, those are effectively its languages, and if they don't share, two different blockchains do not share a common pair, they can't communicate with each other. The interoperability can't happen. So Nervos is the only blockchain out there that you will find right now that supports every single encryption out there. All you need is to come in with a library, and you can use it in your smart contract. That means that Nervos is able to connect to any other blockchain out there, and I don't think you will find any other blockchain that can claim to do the same thing. And then last but not least, re-entrancy attacks do not exist. So this has been in the headlines again recently. We've lost hundreds of billions of dollars at this point to re-entrancy attacks, which are unique to Solidity, but we don't use Solidity on CKB. So fortunately, that doesn't exist on this platform, and there is no equivalent because it would be a double spend. Re-entrancy attacks do not exist. What is a cell? A cell is the most basic structure for representing a single piece of data. So it is effectively like a UTXO. It's composed of 4 distinct fields: the lock script, which controls ownership; TypeScript, which controls state transition; capacity, which is CK bytes; and data, which is smart contracts, state, or anything else. So I'm going to explain these a little bit further. Lock script. So when I said account abstraction, I'm referring to this specifically. A script is just a word that means smart contract. In the cell model, we call them scripts. They're really just a small smart contract. So a lock script is a smart contract that is in charge of ownership. So right, an account is based on a smart contract. This is account abstraction. TypeScript. A TypeScript controls state transition. A more easier way to understand that is it's basically the behavior of the cell. What does this cell do? Is it an NFT? Is it a token? The TypeScript defines that. The TypeScript typically incorporates most of the logic that would be in most typical smart contracts. And capacity, CK bytes. So whenever you want to put data into a cell, and you can put any kind of data you want, you must also lock in CK bytes. Every 1 byte of data that's being stored requires 1 CK byte to provide capacity. So in this context, CK bytes are just and capacity, they're the same thing. In this context, we call them capacity because it's providing the container, right? You want a larger container, you have to provide more CK bytes. Okay, and then data, the last one. Data is just any type of data that can be stored into a cell. This usually is a smart contract, or it's a piece of state data. Like, for example, if it was an NFT, it represents the identifier of the NFT. If it was a token, it's the number of tokens that are held in this cell. And so it can be anything. You can actually put, if it was an NFT, you can actually put the full data. You could put the image in there if you want to. It'd be a little bit expensive, but you could actually do that as well. And so these 4 fields is what constitutes a cell. And all cells are subject to state rent. So when you fill up a cell with data, you are responsible for the state rent. And again, that's where the 1 byte of data requires 1 CK byte to provide capacity. It's those CK bytes that are paying the state rent out of targeted inflation on this actual cell. So when you create the cell, you must make a deposit of CK bytes equal to the number of bytes that it's occupying. And then if in the future, if you don't want this anymore and you destroy this, let's say your NFT is worthless and you want your CK bytes back, you burn the NFT, your CK bytes get released, and you can take those back and you can use them for something else again. Okay, what are scripts? A script is a program that runs on CKB It's a smart contract. So I'm going to go through this rather quickly because you probably won't really be building scripts in this hackathon. You're probably just going to be working with CKBull's tooling. So a script is a Linux compatible binary for RISC-V, right? This is the CKB is just emulating hardware. You could actually take a compiled script, a compiled smart contract. You put it on a Linux computer that has a RISC-V processor, and you could just run it over there. It's the exact same thing. Scripts are used to validate a transaction, and the validation result is a yes or no. So this is one of the things that a script is actually doing is it's just examining the transaction and saying, is this a valid transaction, yes or no? It's not actually responsible for generating the next state, and we'll explain that a little bit more later. Script fields, it has 3 fields: code hash, which is what code to run; hash type, which is how to interpret the code hash; and then arguments, which are arguments provided to the script. So the code hash and the hash type, the first two, these two together basically say what code is going to run, and then arguments are provided to that code for it to do whatever it needs to do to do its job and validate a transaction. So an example of this is the lock script that's responsible for authorizing access to a cell. The arguments would probably be the public key of whoever owns it. So the code hash and hash type would point to the binary that needs to interpret that public key and then check to make sure the user is properly signed for it. And that's how the entire process works. Now, one thing I just got to quickly mention is that a script is 2 different things in Nervos. It's actually a data structure that has these 3 fields in it, and it's also commonly refers to the binary executable itself. And we just know the difference because based on context, like we're saying, we want to execute the script. Well, we're clearly talking not about a data structure, but about an executable. So you just got to watch out for that. Okay, what is a transaction? A transaction in CKB describes a state transition. A transaction contains both the start and end states, and this makes it deterministic. So you already know what the end state is. There's no guesswork. That is an important concept. We'll go through more later. Transactions validate, not generate. And that is also an important concept because validation can sometimes give you an efficiency gain over generation. Transactions have 4 primary fields: input cells, which are the current state; output cells, which are the future state; cell depths, and which are data needed by the transaction; and witnesses, which are arguments provided to the transaction, usually like something like a signature. So input cells are the current state, output cells are the future state. This is part of what makes it deterministic, is because the transaction itself already says what the future state is. And we're going to go through a little bit more of this in the next section. What is the cell model transaction compared to the account model? The account model is contract oriented, the cell model is transaction oriented. The account model generates the next state, it's non-deterministic, it charges fees on failed transactions. The cell model validates the next state, it's deterministic, and it discards failed transactions. So in this graphic here, I'm going to show you an example of how these 2 things would do the same action. So in contract oriented, from the account model, let's say the state value is 5. The transaction, what it contains is a call to the function. It doesn't actually contain any value. It just says call this function to increase. Then executes that, and then the contract itself determines what the next value would be. It would read the state value of 5, increase it, and then write the value of 6. So you don't actually know what the end result is when you broadcast that transaction. You only know that you have sent a request to increase it. So it's non-deterministic. And if for some reason that this contract failed to execute, unfortunately, you'd be charged that fee anyway. And some of us who made it through the bull market, we all know that unfortunately, during the congestion period, sometimes you pay a fee of $50 to $100 for something, and the transaction would just fail. So you wouldn't even get whatever you were trying to buy, and that fee money would just be lost. So in the sell model, it's a little different because it's transaction oriented. Let's start at a state of 5, just like we did with contract. We started at a state of 5. The transaction contains the old value 5 and the new value. This is what you want to change it to. So before you even broadcast this transaction, you know what the result will be. It cannot be anything other than 6. And once this transaction is sent and confirms that value, the old value is replaced with the new value, and the new state is updated to 6. So when the transaction is sent, the transaction, all it does is it calls a validation. And so it's the script's responsibility to analyze this transaction and say, is this transition from the old state to the new state valid? That's what the smart contract is responsible for. And assuming that it says that it's valid, then it goes ahead and updates the state. So this has benefits is that it's deterministic. Before you even sent anything, you knew what the end result would be. And because of that, there's no reason to keep a failed transaction. So any transaction that fails is not recorded in the blockchain. There are no fees for it. What do transactions look like? So this transaction sends 700 CKB from Charlie to Alice. So let's look at just the inputs for now. Charlie has 2 cells. Each one has 500 CK bytes. So Charlie has 1,000 CK bytes in total. This is the current state. So before this transaction executes, this is the inputs is what the current state represents, and the outputs don't exist yet. So after this transaction executes, then the outputs will be what is created, and the inputs, those will be consumed, and they will go from live cells to dead cells, so they will not exist anymore, and they can't be used again, is the new cells that have been created in the outputs, which are the ones that will be replacing it. So you can see from this transaction, what has Charlie done? He's sent Alice 700 CK bytes, and then there's a second cell, which is 300 CK bytes. So this is the remaining. Remember, we started with 1,000 CK bytes, 700 went to Alice, 300 went back to Charlie, right? So that's his change cell. So let's take a very quick look at this in JSON. So what I did is I used Lumos, which is our framework. I generated a transaction, but I actually pulled out the stuff that was less relevant for this example, and I just wanted to quickly show it to you that you can actually see. Here's here's an input cells. We have 2 cells, and you can actually see here's the lock script, which I mentioned had those 3 fields: code, hash type, and arguments. So those all exist. Capacity here. This is actually, you can't read the hex very well, but that's 500 CK bytes. So it's the exact same thing, 500 CK bytes, and then you have the same output: 2 cells, 1 to Alice. We're just using numbers for now. I just replaced these are supposed to be public keys, but I just replaced them with numbers so they're easier to understand. 1 is Charlie, 2 is Alice. This is again a capacity. This is the CK bytes, that's 700 CK bytes, and then down here, here's the change cell back to Charlie, and this is 300 CK bytes. And then we also have the cell depths and the witnesses for signatures. So let's go back to the presentation. Looking at the right side graphic now. So this is to help illustrate again how CK bytes flow through a system and how cells go from live to dead. So we started out with 1,000 CK bytes, and you can see that as we went to transaction 2, we took some of these outputs became inputs, and then they split the cells, and the output became the input in another transaction. So after these 5 transactions have actually executed, you can see that every input that has been used consumed is now dead, and every output that has been used as an input in some transaction is also been consumed and is now dead. So we actually only have 3 cells that are alive. Those are the 3 green cells, and if you add up the capacity of those green live cells, you have 500, 400, 100. That's a total of 1,000. That's the same number that we started with at the very beginning of transaction 1. So in both of these transactions, all of these transactions, these have been simplified a little bit. I've removed the fees just so the numbers add up a little bit or better, but you should get a general idea here. This is all just about conservation and actually preventing a double spend. You can actually trace back where every individual cell came from, including all the CK bytes involved with it. What is the life cycle of a transaction? So I'm going to go through this very quickly. And so this is how we do this in Lumos. This is the normal way of doing it, but you also want to attend the CKBull workshop because their tooling might have some shortcuts for you. So first you create a transaction skeleton. This is just an empty transaction template. It's a data structure that we populate with the values that we need before we execute the transaction. So you add in your input cells, right? This is the existing state that we're going to modify. Then you put in your output cells, right? This is the new state that will exist after confirmation. Then you add in your change cells and transaction fees. So once you have your input and your output cells, then you can actually calculate, do I need change? How much am I going to pay the miners? And you can do that math, and you can create and modify cells as needed to reflect that. Then you add in cell dependencies. These are script binaries and other needed resources, right? It's usually just pointing to the binaries that need to execute the smart contracts. And sometimes it's stuff like Oracle data or something like that too. Then you add the signatures, which prove ownership and authorization to the input cells. This is usually put into the witness field, and sometimes there's other data put in there as well. And then you broadcast the transaction. You send it to the network using a CKB node, and then you wait for confirmation, because as we know, a transaction must confirm, or as far as the blockchain is concerned, it never actually happened. So we're going to look at an example of this in Lumos. So this comes from the developer training course. The L1 DTC is what we also call it. Now, I'm not actually going to recommend that you take the training course right now, because this is not based on CKBull. And also the training course, the full training course, is pretty extensive. It takes most people 2 weeks or more, so you don't have time for it during this hackathon. But I just wanted to quickly show you this bit of code here, because you're going to see that the code itself actually mimics the transaction lifecycle very closely. We created a skeleton. We actually put in some cell depths we did a little bit earlier. Then we're creating an output cell. We're adding input cells. We're calculating the values and adding a chain cell. And then we're putting in our witness placeholders, and then finally signing those witnesses, adding our signatures, sending the transaction to the network, and then we're just waiting for the confirmation to occur. What do I need to get started? So here's a few of the things you need to get started, but you definitely want to attend the CKBull workshop coming up next. So the first thing, get the CKBull mobile wallet that's available in the Android store and the iOS store. You want to get access to a testnet node, a CKB testnet node. You can use a public node or you can use a local node. If you want to use a local node, it's going to be faster and more reliable, but you're going to need to start getting it syncing as soon as possible, because it takes up about 100 gigabytes and takes several hours. So get that going now if you want to use a local node, but the option is completely up to you. Next is testnet CKB. So once you have your mobile wallet up and running, and you have created an account in it, and you have switched it over to the testnet, then head over to the testnet faucet and get some funds into your wallet. And then when you're going to start on your DApp front end and back end, I recommend, of course, the CKBull Signer API, because that's required. And what it's going to work with is I know it's a question mark right now, because I'm not sure what the recommendation is. CKBull has been working on some new tooling and frameworks that they're just about to open source. I don't know exactly where they are, so they'll be making the recommendation for that in the workshop, the next workshop. Make sure you check that out. And then tokens and NFT. Again, you're going to be using the CKBull Signer API, but the CKBull mentors are the people who you want to talk to about this, because they can make the recommendations on how to actually accomplish this with their tooling. I would recommend you start small and expand your scope. Start with the sign-in functionality. Start with a basic transfer, which CKBull will be providing an example to. And then if you really need tokens and NFTs, make sure you get in with the CKBull mentors as soon as possible and get their recommendations on how to handle that. Again, make sure to join the CKBull Telegram channel. That's all I have for you guys today. Thank you all for listening. Make sure you join that CKBull Telegram channel as soon as possible. And then if you need the slides here and you need access to all the links, this is the link where you can access it below. Thanks, guys.
All right. Thanks, Jordan, for a very informative workshop. All right. Now let's move over to the CKBull team.
Okay, guys, are you there? I see you're on screen, but you are not showing your cameras. Do you want to try sharing your screen at this point?
Yeah. Hello, everyone.
Okay, we hear you. Okay.
Let me share slides.
Hi, hello, everyone. Can you hear me?
Yes, we hear you loud and clear.
Hello.
All right. Yep, we can see the slides now.
All right. Sorry, give me 1 minute. I'm setting up. All right. And present that. Okay, can you see my screen now?
Yep.
Great. So hello, everyone. This is Adrià Carrera. I'm the CTO of Persist Technology. Basically, the company behind CKBull application. With me, it's Guillem Garcia. It's one of the main developers of the CKBull Signer API. And here we will try to guide you and explain how the CKBull Signer API works, as well as we will see how to install the CKBull wallet, and also how to develop a D app using the CKBull Signer API. So what will be the content of this workshop? Basically, we'll first see what is the CKBull Signer API, briefly to understand how does it work. Then we will see how to set up a CKBull wallet using CKBull application itself. And then we'll go through understanding the CKBull Signer features. First of all, we will see how the console, the developer console works, and we'll see an overview of it. We will go through the app creation on the console, and then we will explain how the signing process and the transaction process work for doing signing requests and transaction requests. After having said that, we will use the playground that we have inside the console to just play around a little bit using the using transactions and using the API. And then we will provide you a final demo, which is an open source project that we have set up for you that involves all the process, so you guys can quickly and easily check how a D app or how the final environment would work. So first of all, what is the CKBull Signer API? CKBull Signer, it's basically it's a feature on our CKBull wallet that allows an easy and usable connection between the apps and users. As MetaMask do, basically, that you can connect to a D app on a web browser, and you can, as a D app, you can send transaction requests. The user can sign those transactions or reject those transactions. Also, the D app can sign in with the users and so on. So basically, we develop the same features that MetaMask could have or any browser extension wallet could have, but using a mobile wallet. So users are available to connect with the apps using the CKBull wallet, and the apps can secure connections to the users and send transaction requests. So me as a user, I can access any D app with my wallet, which is a mobile wallet, and any D app can authenticate me using CKBull wallet. So the end user would just connect to a web page or a D app, and then the end user will receive a transaction request on their mobile phones. So he will be able to sign those while the D app can check and verify all those processes happening. So first of all, we have to set up CKBull application to proceed with it. You can download it from stores. Here are two QRs that you can use to download either on the App Store or Google Play. I will leave here for 10 seconds if you want to scan those, and if you don't have it. Then we will see how to create a wallet, which is quite easy. We can also import it. And finally, how to fund it using the testnet faucet. So, all right, I'll pass to the next one. So how to create a wallet? This is quite easy. Since this is an app wallet, you will probably seen much wallets before this one. But it's basically you can either create or import your CKBull wallet. Both of those wallets are Neuron compatible. So if you have a wallet on Neuron, you can import it using your mnemonic. And if you want to create a new one, you can create a fresh one. Basically, we will not show that sharing screens because I think it's very trivial. But on Create Wallet, you have you can give the wallet name, and then you have the backup of the mnemonic words. You will be asked after the mnemonic words being shown, you will be asked to type those again. So I recommend you guys to have paper and type those. We are encouraging security here in this step. I know it's a little bit tough when you are setting up those, but you will probably thank that on the future. So after having created and backed up your work, you will be accessing the CKBull dashboard, the CKBull app main page. And yeah, the process is quite straightforward. I will not show a screen in this case because I think it's very straightforward. But Guillem, if you want, you can keep doing that on the background, because after that we will need to show in live how to sign requests and so on. So the next step is connect to testnet and use the faucet. This is also quite trivial. In order to connect to the testnet, you will need to go to the settings, which is a button that you can see on the top right of the screen. And then a general setting, you can see select network here, and you can use the testnet network. This testnet network basically shows you a QR code or an address. You can copy this address, and then you are able to go to the faucet.nervos.org, which basically you can paste here your address and claim CKBs. By doing that, you will be able to send transactions and start interacting with the network. So once you've done that, you have the CKBull wallet ready. This CKBull wallet will be used for you to simulate the end user interactions with your DApp. So it's quite useful, and you will need all those. So once you have everything set up on the wallet side, let's try to understand what CKBull Signer API does, or how does it work. So basically here we have three components. We have the CKBull wallet, we have the DApp, which it's basically what you will be developing, and we have the blockchain, the Nervos blockchain. So how does the sign-in and transaction process flow? The first step is that the user provides the DApp an identification of its account that he's connecting with. I provide the DApp a connection, and I say, hey, here's my address, so you can check my balance, you can check my transaction list, whatever I want to check with my DApp. Once that is done, the account is activated on the DApp. So I've done both kind of a handshake process where the DApp already knows my address and so on. And now as a DApp, I can send transaction requests to the user. So for example, if I'm an e-commerce and I want to ask someone to buy one of my products, I can create one transaction request that will tell the user to send to my CKB account to send me the amount of CKBs that the product is worth it. So once I send this transaction request, the user can sign the transaction. Here it's not showing it's not showing the arrow, but basically the user can sign the transaction, and then the same user will broadcast this transaction to the blockchain. After sending the transaction to the blockchain, the DApp will check the transaction. This is an important step, because the Signer API is not warranting that the transaction has been submitted and it's ready and it's finalized in the block. The CKBull Signer API just shows if the user has signed or not the transaction. The DApp has the responsibility to check the transaction on the CKB, because some kind of bug or error could happen in the middle, the transaction being invalid or something like that. So the DApp needs to check this part. So after the DApp has checked the transaction, finally he can deliver the product to the end user as an e-commerce. All right, so this is the general overview of how CKBull Signer API works. It's quite common and it's quite similar on how a browser wallet would work. There are a few differences here, and for security reasons, we need to authenticate the DApps, because since the DApp is an external service and cannot send transactions in the name of other DApps, we need to have a certain panel or a developer console. That's what we developed and named that as a chain console for the DApp developers to sign in there and just create and verify their own DApps. No one, despite the DApp, can create transactions in the name of the DApp. So the next thing that we are going to view is a console, this developer console for CKBull. This developer console allows any user to create any DApp. Basically, we can go to the link provided on the slides, console CKBull app. I'll log out here. And basically, we can sign in user. Well, we have to create an account. First of all, we can create the account using Google Auth, or we can just add our name and email and password and so on. I won't do this process because it's quite obvious. But we can use Google as well if you want. If you use your email, you will be requested to verify it. So I encourage you to put a correct email. Otherwise, you won't be able to go to the next steps. And well, I'll access with my Google account. So the first thing that we can see here, it's a basic panel where I can see my DApps. Let's say each DApp could be a website or could be an application, decentralized application, whatever we want to. Right now, we're going to see how to create a new DApp. So the first step is to register our DApp. To do so, we can click this button here, and here it is. We will be requested to add some details. So the first thing that we have to do is add a logo, which I will use this one, and we can add here, for example, clothing store, description, whatever we want to. This name, the image, the name, and the description will be provided to the user once he scans and signs in. So all the transaction requests and sign-in requests that will be done to the app will have this clothing store, this icon, and so on. Here we can put an email, for example, info@persist.com, project URL, for example, I don't know, HTTPS clothing.store. Super URL could be the same, and we can provide also terms of service and privacy policy for the end user to be aware of how their personal data is treated. After that, we can create our DApp. So the next thing that the console says to us is that we have successfully created our store, and it provides us an API key and an API secret. Those are two secrets that we need to store as an environment variables, or we have to keep it secret, as the name says. This is very important because anyone with this API key and API secret will be able to make transactions in our name, which is not ideal. Because if we have, for example, a sushi swap, I don't want any user to receive a transaction using the name of sushi swap, right, and on their phones. Instead of that, I just want the users that have done sessions with me to receive the transactions that I want to as a DApp. So I'll pass those to Guillem so he can set up those later on for the demo.
Got it.
Yeah, good. Thanks. So now that we have the API key and API secret, no worries if we lose that, because we can edit our DApp at any time, and here we can regenerate our API keys and API secret. So no problem on that. So now we have our CKBull wallet ready. We have created our DApp. What's the next thing to be done, right? So the next thing now is to try to understand. Let's see here. Great. We have created the DApp. So the next thing that we have to understand is how signing and transaction requests are done. This is where the coding stuff starts. For doing that, we have created one piece of documentation that you can see here. It's on docs.persist.com/CKBull Signer API. We can go to this link, and we can check. Good. And we can check the documentation. So the documentation is basically divided into three modules, let's say. The first of all is getting started. Here, this is what we've seen, how to create an account, how to Google registration or email registration, how to register the app. We already seen that. just if you want to check that, you can see with the doc if you forget anything. Regenerate API keys and yeah, next steps. So the key concept that we have to understand now, it's how signing request and transaction request are done and what they are. So basically, signing requests are requests that are generated by the app meant to identify the user and retrieve its metadata. Transaction requests are requests that are done once a signing process has been finished and basically contain a transaction proposal that is expected to be signed by an identified user. So the first step is to signing the user. Once the user has given me authorization as a DApp, once the user has given me authorization with a signing request, I can start generating transaction requests, and the user will be receiving those transaction requests, so he can sign those one by one. So how does this process work? It's quite simple. Basically, we have here a diagram that explains how does it work. The DApp, it's divided into the front end and the backend. We need this backend since basically we need to keep the API key and the API secret. And this cannot go to the front end because front end, we cannot store secrets there. So we have to create a backend, which will be a middleman or a middleware that will populate these API keys and API secrets in our DApp. So basically, the front end receives an event where a user wants to identify in our DApp, basically ask the backend to generate a signing request. And the backend with the authorization API key and API secret calls to the CKBull Signer API to generate a signing request. The CKBull basically verifies the DApp with the API key and API secret, and just generates one token, which is the signing request generated, and returns the required information to the DApp frontend. Basically, the DApp frontend uses this token generated by the API and shows this token as a QR code to the end user. What the end user can do now is to scan this QR code using the CKBull wallet and basically can sign the transaction identifying himself in the process. After that, the CKBull Signer API updates the signing request status to signed. So the DApp can now see that the user has signed this payload, and the DApp can also check what's the address of the user, what's the network it's connected to, and so on. So this is the life cycle of the signing request. It's quite simple. Basically, once we create one signing request, its status is pending. If the current date it's greater than the expiration date, this signing request is marked as expired and cannot be used anymore. But if the user signs it, if the user ignores it, it just keeps pending. If the user declines it, it's marked as declined, it cannot be used anymore. And if the user signs, it's marked as signed. Once it's signed, this signing request has an expiration date, which is the session expiration date. And once this current date is greater than the session expiration date, this payload is marked as expired. So the session is not valid anymore for sending future transaction requests. Basically, what the user sees once it's signing at a signing request is this screen. Basically, he has to review the connection. Here it's the logo of our DApp that we have set up on our console, the name of the DApp and the description, and signing with this account. The user can, since the CKBull wallet allows multiple accounts per mnemonic, basically the user can check which account to sign with. He can accept it or reject it. All right, having that said, now let's see what transaction requests are. A transaction request must only happen after a signing request. It cannot happen the other way around, because we cannot send notifications to a user that has not given authorization to us before. So basically, a transaction request, it's kind of the same signing request, but instead of authorizing a user to a DApp, what it does, it's make a transaction for the user. So basically, the user flow, it's quite simple and quite the same. Basically, a logged in user with a signing token associated previously triggers a transaction in the front end. For example, a user wanting to buy a product on my e-commerce. The e-commerce front end triggers this event that asks again the backend, I want to create this new transaction. The backend basically prepares this new transaction and creates a signing transaction request. Creates a transaction request. The CKBull Signer API basically verifies the DApp and generates the transaction request, which will be shown to the user and waiting for signatures. So now what the front end of the DApp should say to the user, hey, you have received one transaction request, please sign those. And the front end should keep asking those to the user and making one pulling on the background to check whether this transaction has been synced or not. The user basically consults his transaction request on the wallet. We will show that screen how to access to those quite quickly. And basically, he can now decide to sign it or reject it. All the information of the transaction is displayed to the user, so the user can safely sign the transaction. And once the transaction has been signed, he sends to the CKBull Signer API the hash of the final transaction and the payload and so on. So the DApp, while doing this polling, will now see that the transaction request status has been updated to signed, and he will react wherever he wants to. In the case of our e-commerce, the backend and the front end will perform operations for delivering the product or doing whatever. Great. So the life cycle of the transaction request is quite the same as the previous one. First, we have the pending. If it expires, it's marked as expired. If the user declines, it's marked as declined. And if the user signs, it's marked as signed. Here we don't have the session expired status, since when a session expires, all the transactions are also expired. So yeah, it's quite simple. And here we can see the screenshots of how the CKBull wallet shown to the user this pending transaction request. So we have the activity tab here. Well, first of all, we have the middle scan button that it's used for scanning any QR code on the signing request. This is something that I didn't say before. And then we have the activity tab, which basically has 3 subtabs: pending, signed, and connected sites. On the pending, the user will see one pending transaction, and once you click this pending transaction, this model will show up. And basically, this model will explain the transaction to the user in a user-friendly way. In this case, we are trying to send 120 CKB. This is a transaction fee. This is the account that will be signing that, and so on. And the user can slide to accept this transaction request or reject it. So having that said, we now understand, we have everything set up. We understand what signing request is, what a transaction request is. Now let's go into code itself and see how the API looks like. In this case, we have this module on the documentation called API, where we can see how to authenticate using the API key and API secret provided by the console, and then how to do requests, and finally how to do polling. So the authentication is quite simple. We are also providing here, it's using HMAC SSH 512 algorithm. We are providing here code in JavaScript and Python to generate these signatures. And basically with the header, we are adding the API secret and the API key. It's quite simple. You can very straightforward, JavaScript and Python. The next thing we have to do is create these transactions or signing request. For the DApp that creates the transaction request must use Lumos library. This is very important. It either supports the v0.19 and the 0.18. Not previous to this one. I'm not very sure. It could work, but we don't recommend using previous versions of it. So please use these versions. So you have to just prepare one transaction using the Lumos transaction skeleton. It's quite simple. Going onto the requests, we have the signing request specification and transaction request specification. The signing request, it's quite simple. We have two methods here, one for generating the signing request and another one for getting the information of one signing request. So for generating that, we have to provide signature, API key, timestamp, and so on. And here is the response of generating one new sign-in request. No new parameters is needed here, despite the API key and API secret. And here is what the response of this call it looks like. So we have a sign-in token, which is basically a payload, a random base 64 string. The status of this payload, when is it created, when does it expire, when does the session expire in case that the payload is signing. We have some metadata of this payload, which basically contains the address of the user that has signed in and the network it's connected with, and some information of our GApp. This is the information that we have set up on our console panel. So we have also a method that it's used for retrieving sign-in request. Basically, it contains almost the same information that's shown before. So basically, we first have a post method for creating a new sign-in request, and then we have another method for retrieving this sign-in request, which is this one. Same applies to transaction request. We have one method for generating a transaction request. Here we have to pass to this API call. We have to pass the transaction request itself, which is a Lumos skeleton transaction with all the data that the previous session explained very well. And it retrieves basically we have to pass as well the signing token, associated to the user that we want this transaction to be displayed with. And this API call, it's responding with basically a transaction request status. So this can be pending and so on. And again, we have another call, which is this one, used for getting the transaction request itself, which basically, given a token, we receive the status of this transaction request. If this transaction is signed, we receive the transaction itself with an ID, a transaction hash, and so on, and also the associated payload to this transaction request. So now we have almost all the pieces. We have an extra topic, which is the polling, because when the DApp sends this signing request or transaction request, the DApp must keep asking to the CKBull Signer API if this transaction request or signing request have been signed or have been expired or whatever. So it needs to ask for this status. For doing that, we have created these two methods, the signing token status and the transaction token status, for doing this polling. We recommend using that because it's more lightweight for the API. You could use these ones, signing token request directly, but please use the polling ones. In the future, we will consider adding also WebSockets for not doing this polling and so on. But right now, this is the method that we have. So now we have all the, let's say, all the pieces in place. For doing that, we have two things that will be helpful for you in terms of when developing the app. The first one is a playground that we have created that helps the developers creating new payloads and understanding how this Signer API works. And the other one is a demo that we will show in the future. So in order to use the payload, the playground, you have to go to console CKBull app, where we have to the console where we have created this the app. And right to the bottom, you will see a button called Open Playground, and we can open the playground here. So this is let's say a playground that helps us creating sign-in requests and helps us creating transaction requests as well, and so on. It helps us a little bit to understand how the process works. It was firstly created for us as developers of this console, but after that, we decided to open that to the public, since we think that it can be very useful for you when developing the apps. So once we have created the app and we have gone to the playground, the first thing that we have to do is authenticate. This authenticate, basically here we have to enter the API key and the API secret. Let me grab those from before. This is the API key, API secret. So we can validate that. All right, we have now the verified. So now what we have to do is to generate one sign-in request. We can click this button to generate it. And basically here, we can see our sign-in request. This is the token of our sign-in request, and we have the status here pending. This sign-in request is not associated to an address or a network because it's not been signed yet. But what simulating a final DApp, what it would do, it's basically showing a QR code that can be scanned using the CKBull wallet. I don't know, Guillem, have you been able to share the screen on the mobile phone?
Yeah, I can try to share my screen, but in complete mode. So if you don't mind, I can share it to you. Just give me a second, and I will share it to you. Okay. Can you see my screen now?
No, oh, yes, no, yes. Oh, you're using the simulator?
Yes, I'm using the simulator. I can share my my mobile screen on my desktop, so you can see everything. Okay, so as you were saying, Adrian, you now well, I want to reset the same process, but if you try to generate a sign-in request, I can scan the QR code. So if you can please share the screen and I can scan it.
Is it all right? So is it possible to share two screens at the time? Otherwise, I think we can.
That would be great.
Yeah. All right.
It's possible to share.
Let me share again. I don't think so. Let me share again.
Okay. No problem. Okay, so let me now to share my screen, please. And once done, here you can see. Yeah. Here you can see now how a scan sign-in request looks like in CKB wallet. So here's my wallet. I have some CKB, and as I said before, once scanning a sign-in request, the logo of your app and the name and its description is shown to the final user. So once the user has scanned the sign request, he can choose with which wallet he wants to provide the address to later on generate some transaction requests and sign them. So as we said before, the user can either reject the transaction or sign it. So once the user sign it, he can later. Oh, sorry, maybe fail.
It went wrong. This is the live demo.
Maybe time
session
out.
expired. Have you? I will create a new one because you're
please.
showing session expired. Here. Can you see it?
I will sign it. I'm trying to scan it. I will sign it very quickly. Okay, scan it. Let me now try to sign it. Okay. Now, as you can see, don't stop sharing, Adrian.
Yeah.
You can see now that in the events tab, you can see now that I have signed the request by providing the address, my address, to the API. So now, Adrian, in the section before and the section
below
down of yes, you can generate a new transaction request. In this case, it will be a native token transaction request, passing, for example, transferring 61 CKBs to an address that I can provide to you right now. Let me just share it to you. And this,
great.
and if you, okay.
So
If you generate the request.
Yeah. Now I am able to go to here on events. I can filter the events for transaction request events, and a new event it's happening here. Basically, this event it's associated with the new transaction request token, which has a status pending, and it's going to the address of Guillem's phone that he has scanned. Now, if you can show how to scan this and what the application shows,
Yes.
would be awesome.
Yes. On my way. Just give me a second. Okay. I think I'm sharing now. Can you confirm it?
I cannot see it.
Maybe
All right,
no.
now.
Okay.
Oh, yes.
Yes, as you can see now, here in the tab, activity tab, we can see that in pending transactions, there's a new transaction by the DApp clothing store, which is in a pending status. And if I open or to see the details of each transaction, I can see that is the transaction generated by Adria in the playground with a transfer of 61 CKBs. So here, once again, as the same as a sign-in request, I can neither reject or accept the transaction. If I reject it, it will be wasted away. So this transaction will be expired and it can be undone. And if I accept this transaction, it will be signed and sent to the blockchain once the transaction hash is correct. So as you can see now, this transaction has been signed. And if I want to check or validate that this transaction is added to the Nervos blockchain, I can go to the CKB Explorer, in this case, the Project Explorer, and see that the transaction has been made. As the previous workshop said before, you can check either the inputs and the outputs and the new outputs of this transaction, being the result of 2,496 CKBs in the previous input and generating two different outputs, the 61 CKB that was sent to that different address and the remaining 204,035 CKBs remaining of my UCHO. So once this is done, we can see that in the sign tab, a transaction has been made, which is the previous transaction before.
Yeah. Thank you very much.
This said, this is the process while it's in the transaction.
We can also see here on the our playground, we can see that the payload has been passed as signed, and we have the transaction hash here. What we have to do as a DApp is check that this transaction hash it's already been included in the blockchain, and it has the correct information. So this has not been tampered. All right. So now we have seen how to use the playground, and the next thing is a final demo. We have prepared for you a final demo, which is basically an e-commerce implementation, like a mock the e-commerce implementation using the CKBull Signer API. We have here the repositories. I'll be able to share the screen, the slide story later on, in case you don't get the link. But basically, we have the CKBull e-commerce, which is the front-end side, and we have the CKBull e-commerce API, which is the API, this middleman between the front-end and the Signer API, which is handling the signing process with the API keys. So again, Guillem, if you can share the screen showing how the code looks like, just a little bit, an overview, so the people can understand how this works, and then we can have another demo.
Okay. So, let me just load the code since I closed it to mobile demo. Just a minute. Okay. Just to show, here's the. Let me share the screen. Okay. I hope you can see my screen now. You should be able to see my code editor. Okay, so just to introduce you, this is a simple API that we made to handle some API requests from the CKBull Signer API. As you know, we need to at least have a backend that can handle all the calls we need to generate for our app, just as a signing request and transaction request. So basically, this is an example of how you can build or develop an API using a simple framework as Express, which is a JavaScript framework just to build some APIs, which is very fast. As you can see here, I just have two routes. One is to build a login, which is using the auth headers that can be generated using the code provided in the docs, and just sending this this call to our backend to the Signer API. You can generate a sign-in request. Here also are some more endpoints that you can use to fetch some data and check the status of your sign-in request. And to build the transactions, you can use either some API endpoints that we have provided to you to do some simple calls or simple transactions, just as some native token transactions or some NFT transactions. This code, as Adria said, is able to use by clicking the link to the GitHub repository. Yes. And
please give a star.
You can.
Would be nice.
Yeah. And now I will show you what a possible front-end application looks like and what you can build or use as a template to you. I think I'm showing my screen now. Nope, sorry.
Yes.
Yes. Oh, okay.
Yes, you can see that now. Take some time.
Yes. Okay. So here's just to finish this example, this is another application. In this case, is a React app that you can use to check or to see how it's built. Adapt with an integrated CKBull Signer app process or to sign in with your wallet. This have some components that you can, if you want to recreate or base the app on it, and a final demo that I can show now. Just give me a second that we will show you how a final the app could be look like. Give me a second just to drink some water and let me load it. Okay. Okay, so I think that this is running. Okay, I think you can check now Can you check now my screen?
Yes.
You should be looking at an example of the app. It is just an e-commerce. So what should do this e-commerce to build or to pay with CKBull wallet? First of all, we have to build a login system, which is based on the sign-in request that, as you can watch here, as you can see, when a login is demanded by a user to the tab, it generates a sign-in request. This sign-in request, as I said before, can be scanned with my CKBull wallet, just to provide the data to the tab to know that I'm the user with this address that I want to make some transactions in this tab. What kind of transactions can I do? Whatever you want. It can be some native token transactions as this, NFTs, or token transactions. In this example, what I'm looking for is for a long sleeve shirt that in this case cost me an amount of 120 CKBs. So as an example of a app, this could be the this transaction could be sent to the wallet by just clicking the Buy Now button. And in this way, just sorry, it waits a little. This when I click the Buy Now button, a new transaction request is generated using the sign-in request I have signed before. So, as you said, as you watched in the previous demo, I in my CKBull wallet will receive a notification that a transaction request has been sent to me from the clothing app, and if I sign it, the app can react to this signature by the polling endpoints that we provide to you. So once this is signed, the app can react and throw some events or whatever you want. And this is like an example of how a app could be look like. So in terms of technologies or whatever frameworks you want to work with, we recommend that you just use to build your backend and your frontend any framework you are familiar with, so you can start developing some new features and integrating faster. And in terms of integrating with CKBull calls, like to generate transaction requests and transaction skeletons, we encourage to use Lumos, which is a very powerful library, and we can support even the 0.18 and the latest version, which is 0.19. And with this, I finish now my demo, and I hope you have a very good hackathon. Thank you.
Yeah, thank you very much, Guillaume. That's all of our content that we have prepared. We will be listening to you guys, any questions on Discord and the channels available. So if you need any help when integrating with the CKBull Signer API, or you need any guidance, we can give you as much help as you may need. So please find us in Discord and in all the channels available. And yeah, happy hackathon. Hope that you guys enjoy also the CKBull Signer API and the CKBull wallet. And let's see you in the next weeks with the results.
Awesome. Yeah, thank you guys for going through that. And yeah, as they said, everybody's available to support. You can join the CKBull Telegram channel, which you can go on CKBull Twitter or Nervos Twitter. You'll find it there. And yeah, just ask questions. Yeah, looking forward to kicking this event off, and really interested to see what everybody builds. So thanks everybody for tuning in. And yeah, I think we made it through. It was a long stream, but thanks everyone for sticking around.
Thank you, guys.